Good afternoon. This is a lecture where we will discuss the method of production flow analysis and how it is used to implement design for flow. And design for flow essentially looks at reducing and simplifying material flows. So what is key is the reduction and the simplification of material flows. And that essentially is the foundation for job shop lean. Job shop lean itself is founded on the principles of lean, which were originally put forward by Jim Womack and Daniel Jones. And it has basically 5 steps. The first step is to define metrics of value for the customer. The second step is to identify value streams. The third step is to pick a value stream and achieve flow inside of that value stream. The fourth step is to achieve full scheduling inside the value stream. And then the fifth step is to pursue continuous improvement to keep improving that value stream, and then essentially go back to step one and then identify another value stream and continue. So what is flow? I have taken that definition from Sasaki's book, 1987. So he must have known about that at least 10 years before that. But he defines flow as the progressive movement of products through a facility from the receiving of raw materials to the shipping of the finished product without stoppages at any point. And the reasons for these stoppages could be multiple, So especially in an assembly context, backflows interrupt a forward flow. In an assembly line, you would like all product flow to be in one direction, powered by the conveyor typically. So any kind of backflow will force the forward flow of products to stop while the backflow executes, and then the forward flow resumes. Machine breakdowns, scrap, because every time you have to replace scrap, you are going to have to redo the processing steps for as many units as had to be scrapped. And then there are other production delays. So the idea of flow is like water, water keeps moving. And if it hits a rock, it goes around the rock. If it hits a hole, it fills up the hole and flows over the hole. So personally, I think of flow as similar to how we talk about cash flow, correct? We want our cash to be moving continuously. We want it to be invested. And whenever we have 7 forms of waste, whenever we have production delays caused by the 7 forms of waste, we are going to essentially see our money get blocked. It is not flowing. And when the product you're producing for a customer is not flowing without delays to the customer, you are increasing cost and you're not getting paid for all the investment you're making in that particular order. So I believe that more than waste elimination, designing a manufacturing system and its support services, the supply chain for flow is what is better, and that waste should be seen more as a symptom, as a metric, and not a goal unto itself. So I took my cues for design for flow from this book by Taiji Ono, the godfather, the pioneer of the Toyota production system. And I read through his book at least twice. And pertinent to this particular lecture about reduction and simplification of material flow, I found some of these quotes in his book extremely inspiring and foundational. So page 11, he says, I was manager of the machine shop at the Koromo plant. As an experiment, I arranged the various machines in the sequence of machining processes. That's very important, in the sequence of machining processes. So what he's essentially saying is, look at the routing for every product being produced and ask if the equipment being used to produce that particular product is aligned in the exact sequence as the product would flow through that sequence of machines. And right there you will see that there is that gelling of the concept of functional layout against cellular. Page 33. We realized that the Kanban system would not work unless we set up a production flow that could handle the Kanban system going back process by process. So there's a connectivity that he thinks is very important to be set up. And usually when we design a layout, that's the connectivity we would like to set up, where consecutive equipment requirements are adjacent to each other. But what he's getting at is that production in an inventory control cannot be done very effectively if you do not have systematic streamlined material flow in the first place. Page 39. It is undeniable that leveling becomes more difficult as diversification develops. So what he's again getting at is that it is nice to be saying hijinka and mixed models production and load leveling, but as you make a variety of product, that becomes very hard to do because typically the demand for those products tends to taper off very quickly. There'll be a few product variants which are in high volume, and then most of them will be low volume. So leveling production as opposed to make to order becomes a challenge. Continuing on his book's quotes, Toyota's main plant provides an example of a smooth production flow accomplished by rearranging the conventional machines after a thorough study of the work sequence. Again, that is what we all do in facility layout. We look at how the different products routings align with respect to each other. And the challenge is all the equipment for every one of the products aligned exactly in the sequence of steps that the product will follow as it gets made. Next quotation. It is crucial for the production plant to design a layout in which worker activities harmonize with rather than impede the production flow. So this is looking at respecting the design of workstations and how individual workstations sometimes get arranged into U-shaped layouts, because when work cells are designed in a U-shape, employees work uninterrupted inside the U and all logistical support to the cell occurs outside the U. Another quote, by setting up a flow connecting not only the final assembly line but all the processes, one reduces production lead time. There again, what he's saying is that the total time it takes you to make the product, for the product to go travel from raw material to finished product, is implicitly connected to the overall structure of the factory, which is that all the components and sub-assemblies, as you track their movement through various pieces of equipment, they're all aligned and they deliver products to different points at the point of use on the assembly line. Page 123. When workflow is properly laid out, small isolated islands do not form. And think back again when there is this debate between functional layout, putting all equipment into departments where similar identical equipment alone is put in each department, as opposed to work cells where equipment is taken from different departments and co-located in an area where now the work cell takes charge for starting to produce from raw material to getting the finished product in one area. Next quote, for the worker on the production line, this means shifting from being single-skilled to becoming multi-skilled. Once again, if you co-locate different pieces of equipment into a work cell, automatically you are going to have to train the employee, and the employee will need to get trained and cross-trained, be multi-skilled, in order that they could take raw material and go through steps 1, 2, 3, 4, 5, as many as needed to complete the product. And that requires a high level of cross-training. So personally, the future is about better skilled employees, and not saying that, oh, you know what, we are going to look at job loss. I think there'll be a bigger demand for education and training of employees to work in a more high-tech environment. And finally, this last quote. The first aspect of the Toyota production, right, means putting a flow into the manufacturing process. Now, We place a lathe, a mill, and a drill in the actual sequence of the manufacturing processes. So that is very, very fundamental. When you look at things like value stream mapping, uh, implicit even to those methods is this underlying emphasis on, have I aligned the manufacturing equipment and the overall factory per the logical coming together of the components, the sub-assemblies, and the final product? That is what is fundamental. And I think that's what's actually missing in the way US manufacturers have designed their plants and how uh, Toyota seems to be thinking about the way they build their factories. So here's the quick question, that if, if you saw this flow, and this is about 500 plus different components wending their way around in a forging facility, and they made large forgings for submarines and ships, power generation equipment. This is a spaghetti diagram. So when you see a spaghetti diagram that captures the actual material flow of many products in any facility, you should immediately know that there is no way that this facility is demonstrating flow of material. There's clearly a lot of delay, a lot of batching, a lot of absence of visual management, and this is essentially what happens when you go from assembly line manufacturing to any other kind of high mix manufacturing, be it low volume or high volume. So this is one forging, right? So previously you saw many forgings paths being mapped. Take this one forging, right? Right now, you can see if you looked at this kind of spaghetti, once again you would know that when some product is traveling long distances between consecutive operations, there is crisscrossing of material flow inside the same building, across buildings. There is no way that this facility is waste free and delay free on any order that it tries to fill. Again, this is a forge shop, so it becomes even more challenging because they tend to have monuments, big presses, they tend to have heat treatment furnaces, which are process or batch production type of equipment. You just don't get one piece flow. And then when you have these large travel distances, communication is poor, scheduling and shop floor control are challenging. Again, a simple spaghetti diagram will tell you quickly whether or not the facility layout is designed for flow. And if it is not designed for flow, then you should understand that there is a lot of cost and delay built into its efforts to fill customers' orders. This is a value stream, and again, I find the value stream map as a very good mapping tool. I think it has a lot of merits, and the most important part of the value stream map is it captures all the production control, shop floor control, scheduling, purchasing, supply chain management aspects of the typical factory floor operations. And you can see again that with the value stream map, we're essentially capturing a value added ratio. The value added ratio is essentially the sum of all the value added time. This is typically the labor time that gets charged to a particular order as it bends its way through various pieces of equipment. And when you divide that by the flow time, which is the total calendar time that that same order spent inside the facility in some or other stage of processing. So when you see numbers like this, that's essentially saying that there's a lot of waiting and material handling and other delays occurring that are making it hard for this particular manufacturer to be able to quote short lead times and quick response to any customer. So why do I personally consider flow as important? I believe that with flow, you are looking at total time in the system. So it's the progressive movement of products from raw materials to the shipping, right? I feel that if you worry about the total time that any order spends inside the facility in process, that's way more important than worrying about, oh, let me go and pursue waste elimination as a strategic objective. So in my personal opinion, I feel that If we focus on material flow, faster, better, cheaper, and we design systems and processes and support services on the principle of flow, implicitly the occurrences of the different forms of waste is going to be minimized rather than sort of start by saying, okay, we are going to pursue waste elimination across the enterprise, and then you do what is called continuous improvement by whack-a-mole. You just everybody's doing a little bit thing, and then somebody's improvement is coming in the way of somebody else's improvement. So personally, I feel that waste elimination is not recommended. Design for flow is recommended. And you've probably heard of Little's Law. People might say, well, for this reason you can't apply it, and that reason you can't apply it. That's just mathematics. I think at the end of the day, this is pretty much a very valid formula. It basically says that any order, the time it spends inside a system is going to be how much work in process you see in the system divided by the average time it takes, or that is the number of products you produce per day. So it's a work in process in total dollars divided by how much you're producing per day or shipping per day, dollars per day. That should tell you the average time that an order spends. And again, I think that Little's Law gives us a common sense strategy to eliminate waste, lower costs, and increase order fulfillment on any given day. And the bottom line should be reduce the average time it takes us to fill an order, period. Why aren't we able to do that? Why do we take so many weeks to complete an order? Can we bring it down by a few days? Can we bring it down by a few more days? And if we focus purely on what can we do today to bring down the average time that it takes us to complete an order, we will be on our way to being lean, to being quick response, to being flexible. Again, that's just a personal opinion. I think that Little's Law pretty much gives a mathematical justification to this management consulting goal of, oh, let's eliminate waste. And of course, these are 7 forms of waste. And again, when waste increases, the delays due to non-value adding work increases, and that increases the flow time. Okay? And so I think that when Shingo or Ono, whoever gave us these 7 forms of waste, they really helped to crystallize how we do non-value added work and how we should be looking to quantify the non-value added work. So sometimes they use this acronym downtime or TIMWOODS, but these are 7 ways: correction, operator motion, producing product and then leaving it in a warehouse, transportation, any form of work in process, over processing, you take too many steps, too much setup time, very high cycle times, and of course, waiting. So there are 7 forms of waste, and they really help to crystallize and measure why it is taking us so much time and dollars to fill an order. I think it's again very important to understand that the wastes translate to delays in flow time. So this is an example again that connects time and inventory. It's taken from a book written by Ed Phillips, very good consultant. And what he was again getting at was that the more time it takes you to fill products, the more inventory you hold, and the more inventory you hold, you basically pay a higher carrying cost. So the less inventory you hold, because you are getting orders out faster, better, cheaper, the more you're cutting back on the overhead cost. This is again a timeline diagram, and the thing is that again, when you perform activities on an order, it's either value-adding activity, necessary but not value-adding activity, and non-value-adding activities. And when you look at this timeline, you can essentially take every activity and put that as a duration on a discounted cash flow timeline. And accountants may have better ways to quantify the total cost accrued of any order as it runs its way through the shop. So this point, this is the investment of the raw material on the order. Then it is carried in the warehouse as pure inventory. It's a carrying cost. Then there's a uniform time series as the material handler moves it for whatever distance and time it takes him or her to bring the material to the first machine. Then the raw material waits in queue. Then there's so much amount of setup time that the operator spends and the machine is idle to prepare. Then there's a cost of processing at operation one. Then that batch waits to be picked up. And then it repeats and this continues. And so when you look at all these activities and you reduce them to point cash flows or uniform series cash flows, you can compute something called a future worth. And that future worth is the true cost of an order that oftentimes, because accountants and estimators are not factoring in the 7 forms of waste, they may be underquoting on their margins to customers. What has come out for sure over time is that, and this was a chart which was created by Professor Eugene Merchant, who is recognized as one of the gurus of metal cutting. And this was in the 70s that he created this timeline. What he said was that when he looked at, empirically, when he looked at the total time that a machined part spends inside a machine shop, 5% of that time was spent actually on the machines, whereas 95% of that time in the facility was spent in moving and waiting. And these are 2 of the 7 forms of waste. What was interesting was he came back and said that even that 5% that part spends on the machines, only 30% of that time it's actually having work done on it. Metal is being removed. The rest of the time is basically necessary, but it's preparatory work, but the part's not gaining value. It was pretty interesting that back then in America, somebody had recognized the connection between lost time and cost and order fulfillment. And this was in machine shops, not a big assembly line like Ford. So when you want to connect how factories are built to get good flow and the total time it takes to complete an order, here's what I would say the chain, the domino effect. So when a facility layout has badly designed, where you have not factored in the placement of the equipment to conform with the actual processing sequences of the different components and sub-assemblies, you will find that the average travel distance per order is high. When that happens, the transportation waste is high. And when transportation waste is high, the work in process waste is high. When work in process waste is high, waiting waste is high, which implicitly results in flow times being high, throughput, orders completed being low, and the overall operating cost of the facility being high. So there is no mathematical equation here. It's kind of empirical, but the point again is that if you are not flowing the product because you've got large travel distance of separation between consecutive operations, end of the day, you're not going to be profitable, because recall what Goldratt had said about the 3 primary metrics that should run a business. Have you got high throughput, sales dollars? Have you got low inventory costs? And have you got low operating expenses? If you haven't scored high on those 3 goals, you're not running a profitable business. How do we connect facility layout and working process, which is basically travel distance and the effect that has on batching? Again, this quote came from this book, 1990, and it very simply said, if successive processes are immediately adjacent, as in an assembly line, a single unit is moved at a time, right? So assembly line, single unit is moved. So that's the lowest amount of inventory you can have. Now, put the 2 consecutive operation equipment across the aisle. That's about 14 feet, correct? So now you cannot have the operator from one machine, after they finish one part, immediately walking across and giving that part to the next machine across the aisle. So what they do is they do a handling lot size is a unit load. So they will either fill up a pallet, let me say it's a batch of 50. They will those raw material pieces like forgings or bar stock will come on a pallet as a batch of 50, or they'll come in a container as a batch of 50. What will this machinist do? Only when they finished all 50 parts, then they will bring a pallet jack or a forklift and cart that container across the aisle to the next machine. So the moment that the distance went from 6 feet to about 14 feet, the transfer batch size went from 1 to a container. Now, if you increase the distance even further, if the next process is across the plant, the handling lot size is at least an hour's supply. So your batch size goes up. And when batch size goes up, working process goes up. When working process goes up, your queuing time, your travel times, and your throughput delays increase. Okay? And then if the next process is in another plant, the handling lot size is at least 1 day's production. So implicitly, the increase in work in process costs are directly related to the travel distance that is recorded and experienced by any part. So this is a simple inventory triangle. So the x-axis is the total time that a process is running before the inventory it produced is pulled away to the next process, right? So the x-axis is time and the y-axis is inventory. So this case is where a lot of inventory is built up before that batch size is moved to the next machine. And this case is where you have shortened the travel distances, and now you are able to operate in the mode of transfer batches. So the machine runs for some time, it creates this inventory, and that quantity is immediately moved to the next machine. Once again, the machine keeps running, so much inventory is built up, once again it is flushed to the next. So even though this plus this plus this plus this is equal to this, so the quantity produced is what is needed, but the buildup of inventory is going from a batch size to transfer batch size. So there are 4 transfer batches here that effectively equate to 1 big transfer batch. And when you reduce travel distances between consecutive steps, you will have this ability to make some, move some, make some, move some, which implicitly will bring down the work in process cost and the costs associated with the batch production. So how do we reduce these wastes, right? So we know that transportation and weighting and inventory are significant forms of waste in any production environment. So how do we reduce those dominant wastes? That is where this concept of design for flow came. And again, I'm not the first one. This is not unique to me. I just basically adapted this from Tompkins textbook on facilities planning. It's they mentioned this or discussed these ideas early in the book. So there are 3 principles: you minimize flows, you maximize directed flow paths, and you minimize cost of flows. So you see, nowhere have I mentioned anything about waste elimination, because personally I believe that through good layout, efficient material handling, smart storage systems, good production scheduling, and effective shop floor control, you implicitly will be doing the things which will minimize the 7 forms of waste. So the more important thing is to be able to implement these principles and reflect them into the design and operation of the production system. So how do you minimize flows? You eliminate operations, you combine operations, you try to do multiple products which should go together in one trip. Second principle is you maximize directed flow paths. So this essentially comes from the assembly line concept, and we pretty much do that by eliminating backtracking and reducing cross flows. And then finally, when you do have to move material, you minimize the cost of moving. So when somebody uses gravity to move material, you are eliminating the need for somebody to be told, get a forklift truck, drive to this location, pick up the product, and take it to the next location. And so implicit to design for flow are all these industrial engineering skills or functions, time studies, setup production, cross training, facility layout, material handling. And so I personally push for implementing design for flow. And I use design for flow in combination with the 5 principles of lean put forth by Womack and Jones, except that the tools used to implement the 5 principles are more aligned with high mix processing and not repetitive assembly line processing. So next, what I will discuss is the ways in which you implement these 3 principles. And again, all of them are discussed in other sources. So I'm not going to spend time on discussing each of them. The better thing to do would be to just email me or give me a call or any other form of communication and say, I would like to know, how do you implement this particular principle? Okay. So some strategies to minimize flow. Remember, the first principle was minimize flow. So on this slide, I discussed these strategies. Again, it could be the way the layout is designed, it could be in the way the product is designed, it could be the technology which you use to process the product. Some more strategies to minimize flow. So, combine several transfer batches into unit loads. Some people might say, is that good practice? It depends. It all depends on the feasibility and the particular situation. This one, eliminate outlier routings by rationalization of the product mix. The more that multiple products can be produced on the same flow line, or the same cell, the better you're able to minimize the number of different operations being performed to produce a family of parts. So that is what I mean by rationalization of the product mix. In some cases, you might eliminate the product and say, why are we making this special variant when we are not really getting much profit and much volume of that particular part? Very important to minimizing flow is prevent proliferation of new routings. And especially in the small, medium-sized companies that are make to order, they really don't keep track of the fact that many times they may be doing from scratch, designing from scratch, planning from scratch, the same part or variants of it. And if they put some more time to control how many unnecessary drawings and tooling packages they're designing, implicitly you will minimize the flow of product. So then the second principle is maximize directed flow. So in this chart, I discuss how to recognize a good and bad directed flow. So if you create a spaghetti diagram, that might be a better context in which to discuss the different types of flow. So forward and in-sequence flows in one aisle are the best. So imagine this is an aisle, right? It separates 2 banks of machines. So if you are sending parts from machine to machine in sequence, that's perhaps the best forward flow you can have. Okay, so what's the next relaxation of good flow? You allow flow to occur to machines across one aisle. Okay. So forward flows between parallel and adjacent lines of machines separated by a single aisle are okay, right? That's the second. And then, of course, the worst cross flows are where you can see that one part literally jumps across one aisle and goes to a machine in another aisle. So spaghetti diagrams, if designed correctly and comprehensively, will help you to quickly see if your facility layout and your product mix and your manufacturing sequences combine to have good directed flow or poor directed flow. So again, how do you maximize directed flow paths, which is the second principle of design for flow? Again, these are various strategies. These are almost like individual lectures sometimes, so I will not spend time on them. If you have interest, please email me and I'll be happy to discuss a specific strategy. Okay, and you've heard about U-shaped cells, you heard about W-shaped cells, S-shaped. Again, it's all built around compacting a linear line and allowing or fewer people to work safely inside a secured zone. Um, I believe personally that the 26 letters of the Roman alphabet, A, B, C, D, E, F, G, H, each of them represents a certain flow pattern. And the challenge, of course, these would be NP hard problems, is once you have a hospital or a warehouse or a machine shop or a fabrication shop, once you have the flow network captured, say, as a from to chart or a product process matrix, how do you fit that flow onto one or more of these alphabets to decide that, okay, this is the best flow I can get, and this will be the ideal arrangement of my equipment to get flow in the facility. I think the most important thing is, look at the products you make. If there are assemblies, then please make sure that you develop what is called the operations process chart for the entire product. These are standard charting methods taught in any industrial engineering textbook on methods analysis or facilities planning. The difficulty is that they get pretty hard to analyze visually and manually. And that is, again, an opportunity for today's operations research and data science methods to help us solve. So finally, the third principle is minimize cost of flows. So again, a whole bunch of strategies, lots of explanation. Uh, just give me a call and we can discuss. Same thing. How do you minimize the cost of flow? You just minimize how much space you leave between machines for one process to just fill up the work area in front of the other process. So finger theory constraints and drum buffer rope scheduling, while they may not be very mathematical, they're very effective to implement. And it doesn't take rocket science to know that, especially if you have a linear production system, if you find the bottleneck and then you subordinate the entire system to the rate at which the bottleneck processes product, you automatically control how much raw material is pulled by the first process step and processed and becomes work in process in the rest of the system. So a lot of these, strategies, there are combinations of production control, scheduling, material handling, and facility layout, and of course, the type of equipment you have, and of course, the way management policies drive how people run their machines and whether they do single piece flow or transfer batch flow or batch production. These guidelines came from Professor Apple's book, 1977, one of the inspiring textbooks on facilities planning, because Professor Apple demonstrated both a knowledge of operations research and practical industrial engineering. I can't say that about current books, but in all of these principles, I believe that uh, each of them guides you to design a factory and operate a factory and use material handling systems and shop floor control systems and technology that at the end of the day basically says faster, better, cheaper, waste-free production. So once again, I cannot say that it's clearly known how to use which combination of guidelines. I would advise you to use these guidelines as a checklist of sorts. Okay, so I have a Xerox copy of his book, and I've always, after design the layout, got together with students, got together with clients, and said, okay, let's take this checklist and let's ask ourselves, have we achieved a large number of these guidelines, or do we have a glaring omission of a couple of those? So please understand that I think we in America did know how to design good factories. Somewhere we went towards efficiency as opposed to effectiveness. And then today, everything we do is driven around what Toyota does. Because somehow it seems Toyota figured out how to take such knowledge and use it correctly. Again, these slides are obtained from Ray Keefe. At that time, he was the vice president of manufacturing at Emerson. But what he basically said was the product design, what we do to do design for manufacture and assembly. If you design the product efficiently and effectively, you implicitly will be able to minimize the amount of effort that has to be put in to flow the product. So think of it this way. what essentially is doing with DFMA, design for manufacture and assembly, is optimizing the first principle, which is minimize flow. So when you take, say, a welded fabrication and you cast it or you 3D print it, you effectively are eliminating all the wastes and delays that come from having to make different components and coordinate them and fixture them and then weld them. So it's pretty fascinating, but it makes complete sense that you don't want to rely purely on factory design and operation to minimize the cost. Much of the cost and the waste is going to be in the product design and the technology used based on the product design. Some more strategies. So, how do you implement design for flow? For years, I studied this method called production flow analysis, and you can see again that flow is a common word between design for flow, production flow, and 7 forms of waste created by bad flow. And of course, the metric we want to optimize is flow time. So, in my experience, I found that implementing production flow analysis across the enterprise at all levels of the enterprise implicitly results in a production system design for minimum waste and rapid flow. So what is production flow analysis? It's a technique. Originally, it was designed as a technique for machine grouping, part family formation, cell layout, and overall factory layout. And it was developed by Professor John Burbidge. And the beauty of this method is that it's used for factory design, but the way it's applied is in 4 stages, and each stage is progressively smaller. But in each stage, he's looking for flow. He's looking to minimize flow, maximize directional flow, and minimize the cost of flow. And so it is done in 4 stages. The entire factory, each shop in the factory, each cell inside the shop, and each machine inside the cell. That's amazing, very well structured. So there are 4 stages. Factory flow analysis develops a unidirectional flow system joining the various departments. So we'll see an example later. And each department completes all the parts it makes. Then there's a step called group analysis. This looks at each shop. Then there is line analysis. That looks at the flows in each of the cells that's formed by group analysis inside each shop. And finally, there's tooling analysis. The movement of tools, the movement of the operator, the movement of the part, the movement of the gauges, the fixtures. You're trying to basically minimize flow delays and flow costs at each machine. Tooling analysis also could be thought of as seller production, which is a very Toyota specific improvement method. And then what I found over the years was that it was important to understand that the shop layout had to have violations of the cell concept, especially if you had monuments, if you had expensive machines which could not be put inside each cell. So there is this need to understand how inside a shop you may not be able to get a perfect cell layout, and you would have to have something called a hybrid cellular layout. So what's the first stage of factory flow analysis? You basically look at the individual departments that comprise the entire factory. So you can see that this is raw material. This is where we do sheet metal work. This facility, the shop does the forging. There's a welding department, a machine shop, there's assembly, and then of course the vendors. So you're looking at how product flows between big areas, the big departments, the big shops. And then oftentimes, the best way to simplify the factory flow is when you combine large departments. There are many ways in which you can look at factory flow. Some approaches is being design-focused factory. So they segment the product mix by volume and revenue and demand stability. And then they design 2 or 3 mini factories and that. But essentially in factory flow analysis, what you're doing is you're trying to minimize the back and forth movement of product between the shops, the departments. Okay, that's the first stage in production flow analysis. The second stage is the classic cluster analysis mode. and that's called shop flow. So in shop flow, what you're doing is you're taking all the machines, in this case, if you have a machine shop, taking all the machines, you're taking all the parts. Each X represents that this machine is being used by this part, right? And then you reorganize, you're reorganizing using cluster analysis techniques. So the same matrix now looks like this. Same machines have been ordered this way, and some of the machines have been duplicated. The same parts have been reordered this way. Now what you're seeing is what is called a block diagonal form. So certain machines make certain parts. Certain machines make certain parts. And you see these exception operations, you will find in most applications, no matter how good your clustering techniques, just the way the product mix is set up, just the way the routings were designed, there'll be a lot of outside operations. So in these matrices, these areas are going to be full of ones, and these partitions will sometimes not be very easy to figure out. And to me, in a high mix environment, this phase of analysis actually becomes a large continuous improvement process where you start saying, why should a particular part have to go to other cells to access or utilize machines? Why couldn't that machine be inside the cell? Why is that machine even necessary? So the second part is in many ways almost like a visualization of hundreds of value streams. So you've heard of value stream mapping. In a typical map, you draw just one routing, and you don't even know if that routing represents a product family. Imagine if you didn't have to draw a value stream map with all those icons. What if you were to visualize multiple value streams? I think that this matrix representation is that alternative representation where many value streams that share machines, common assets, are being shown together. So this is the second phase of production flow analysis. This is where you try to minimize material flow and increase the product family manufacturing inside a particular shop, like machine shop, sheet metal shop, forge shop, weld shop. This is cell flow. It's also line analysis. Essentially what you're saying is, inside the cell, how should I arrange the equipment so that I have continuous transfer of product from one machine to the next, so that one person could oversee at least two machines, so that the cell does not have to rely on outside services and support. It could have its own internal assets. So that's the third phase of flow improvement. In this case, you're focusing on flow improvement, design for flow inside each cell. And then finally, you have what is called tooling flow analysis. So here, what you're doing is you're taking a family of parts and you're creating something called a composite component. A composite component is one component which has all the operations which are needed to make all the parts in a particular part family. And then you tool the machine to produce this particular part. That way, simply by indexing the turret head, you are able to bring the appropriate tool to work on the particular part. And imagine this right today with machining centers which have tool magazines which can hold hundreds of tools. You can basically take a 5-axis machine, tool it for a family of parts. That same machine has a pallet changer, and each pallet has different parts, and that's how you get lights out machining. All the programs, all the tools, the fixtures, everything has been set up. You hit run, the programs automatically execute. The program knows which pallet has which part, and that's the amazing part, that with tooling analysis, you're looking at how can a particular machine's utilization be optimized, especially in today's time and age when you've got a level of automation and monitoring that's unbelievably sophisticated. This is the second form of tooling analysis. This is where you try to understand all the setup requirements and tooling requirements, surface finish requirements, and you actually estimate parts and you design tooling families where you say a particular group of parts in a cell should have their tools and gauges available in one cabinet. Another set of parts should have their tools and gauges and other accessories they need in another area. So When you make parts, you can see that there's a whole, there's fixturing, there's size issues, shape issues, there's feature issues, there's boring issues, and then you have material condition, you have surface finish and accuracy condition. So all these factors combine into the eventual design of the tooling, the fixturing, and the machine set. So that's production flow analysis. Factory flow analysis, shop or group flow analysis, line analysis, which is flow inside a cell, and then tooling analysis, which is essentially optimal movement of man, machine, tools, and product at a particular machine. So how could flow be applied to the entire enterprise? Think of it this way. Any OEM's factory could apply production flow analysis in 4 stages, right? Then they will have their sister factories or their supplier shops, right? And you can essentially apply this reduction flow improvement to any factory, any supply. And so that's how universally applicable I found production flow analysis and design for flow to be, to basically implement the principles of lean and to pursue waste elimination more as a metric rather than as a goal. But in all of these, single machine, cell, shop, factory, all of the other facilities in the enterprise pretty much would be organized that way. And then each of them will have their own suppliers. So each supplier could essentially have this approach implemented to improve their operations. And that's the software. Again, I'm not here to sell software. All I'm getting at is that being industrial engineers, we learn operations research, and now we have this whole area of data science and machine learning. I believe that the time is right for us to get away from the 20th century, lean tools which were manual. We use things like 5S and setup production and single piece flow cells and spaghetti diagrams and value stream maps. Today, with the amount of data that we have available and the capability with software packages like Python or R or Mathematica to analyze this data, I think that we can apply the algorithms of production flow analysis extensively. It's just a question of, pick the area of the business where you want to apply it and run with it. So the beauty of the FAST software is that over the years, I found that different outputs of the software can be used to implement these individual improvement strategies. And I call them LATs, Lean Advisory Tools. So you can see on the slide, there are various improvement projects that you can do. So you don't just jump into a factory and say, oh, I'm going to apply production flow analysis to be able to implement design for flow and lean. There's ways in which you can break down the overall improvement plan into these individual projects, and then cascade them in an appropriate sequence depending on what problems your facility is encountering. So there's some success stories. This was just overall production flow, factory flow analysis. This was a Ford shop. They had monuments, red machines. There was no way we could implement cells, so we implemented these things called modules. Each module is a collection of other machines around the monument with the sole purpose of eliminating a lot of the large travel distances which you see in the original layer. This was a modular layer design. This was a welding cell. They sent us and these were a lot of aerospace engine components. And with the analysis we did, they were able to implement this welding cell. This is a high mix machining cell. Again, this came from a book in which the authors gave the data, but they never actually showed how the layout should be designed. And over the years, I've kind of understood why they didn't do it, because the routings are very dissimilar. And you cannot fit all the flows into a nice U-shaped flow line like arrangement. So this is almost like a hybrid flow shop, right? So why is it hybrid flow shop? You've got three stages of the shop, right? And there are different machines in each stage. So stage one, stage two, and stage three. And because you want short travel distances between all machines, because stage one has many machines, it's kept into like a varied arrangement, and then here you're allowing one person to work on at least two machines. Okay, so that's a flexible machining cell, many different parts, many different routings. Personally, over the years, I've kind of come to the conclusion we should not have put all those parts into one part family. They didn't belong together, and that this is too complicated flow for us to be claiming flexibility. But again, with today's technology where multiple machines can be combined into one machine, who knows, it would still be possible to have this cell operation. This is finished machining of castings. So this was in a foundry that was later closed down because of environmental violation. This was in Columbus, Ohio. But what you see here is the absolute chaos in the finished grinding department. And people were having to pick up and move castings by hand. So when we took the from to chart and we designed this, the best we could do was, you see all these heavy traffic flows. At best we can, we put the workstations kind of in a three-line arrangement, and people at least did not have to move product very large distances. Once again, much more could have been done. I don't think flow alone is a solution for this kind of finished grinding cell. This was a pipe fabrication job shop, and one of the failure projects that we had, again, you can see that the biggest issue was they had a single common wash tank. And so no matter what pipe they produced, in whatever quantity, since it had a lot of cutting oils on those pipes, they would run them to this monument. And even though we implemented work cells and we create modules, it was not the right solution. When we walked away, we told management that we don't think layout is a solution. You are just not going to get good flow. The bigger thing was to understand their business and to accept that they could not be in the business of making any pipe in any quantity to any due date for any customer. There had to be a reining in and a strategic plan as to what types of pipes they would fabricate, what kinds of quantities they would accept, what kind of pricing they would have, and then to train their salespeople to be a little more strategic and considerate about when they negotiated an order. Failing which, we kind of walked away from this particular client because layout was not the solution. You can't have a complicated factory logistics and try to be lean and flexible. You have to simplify. You have to streamline. This was a Metal Toledo. This was a scale. They make those large industrial scales that weigh the 18-wheelers of highway. And what you see here is the layout we proposed to them for their fabrication factory. And the way that the factory was designed, this was a violation, and a little bit of this was a violation. But unfortunately, because they had built the facility several years ago, they were like, well, thank you very much for your ideas, but we are now going to undertake to rearrange this facility. And I think that is why design for flow is so much of a design goal by itself. We've talked about product design as a means of, reducing the costs and delays of bad flow. I think that the way you build the factory from the get-go is also important. So many companies just take this attitude of, yeah, just put the equipment in process arrangements and, we'll figure it out. And then for decades, they are stuck with costly material flow and material management. So this was designed using the bill of materials and the operations process chart of the entire product. And this case study is actually discussed in my lecture on value network mapping. That's about the end of my lecture. A lot of this work was done when I was supported by the Forging Defense Manufacturing Consortium and the Defense Logistics Agency. And I haven't given his name here, but there's a gentleman named John Turpak. He was the director of the Forging Defense Manufacturing Consortium, and he funded all my research on design for flow and job shop lean and the FAST software for 8 years, 2004 to 2012, before I left Ohio State. So this is again acknowledging their support to make job shop lean a reality. These are all the partners we had. At that time, pretty much I had worked with all these forging companies. And these two gentlemen, Dr. Rajiv Ramnath and Dr. Rajiv Shivpuri, again, very big supporters of my work. National Science Foundation funded so much of my research. And this gentleman, John Turpak, is, I would say, somebody I'm eternally going to be grateful to. What is important to understand is that when you go in and say, I want to implement lean, personally, if you look at the principles of lean, they tell you to solve 3 major industrial engineering problems first. Okay? Find your product families, design the facility layout to conform to the logical flow of products in each of these families, and then try to schedule production subject to finite capacity constraints. So part family formation, facility layout, and then production planning scheduling. These are classical, well-known industrial engineering areas of study and expertise. And you can say bye-bye to a lot of things like waste elimination and single-piece flow, and basically reduce lean manufacturing to hardcore industrial engineering problems. Thank you.